Research on motion stability control algorithms of multi-action introduction robot based on deep performance learning. The contents include four parts. The first one, research introduction. Abstract. When the multi-axis introduction robot is disturbed by the outside, such as noise, duration of heading edge, time conclusion, motion control, and long one, we adjust distance. Mutation stability control occurs of multi-axis introduction robot based on deep reinforcement learning is proposed. Designs and structural characteristics of multi-action introduction robot consider that the forge postation can reach the expected motion rate and optimize the motion trajectory planning mode of multi-action introduction robot according to the expected moment speed and angel velocity of the center of mass specification. Artifactually in advance, the positive vector of the normal foothold of the foot end of the multi-actual introduction robot is calculated. Based on deep performance learning, the dynamic equation is constructed and the motion stability control algorithm is designed by describing the change rate of the moment of the center of mass. Experimental results show that the proposed method has good fault tolerance of mutation stability control and can effectively improve the accuracy and effectiveness of mutation stability control. The key words is how five words. Introduction for the multi-action introduction robot, stability refers to the ability to maintain stability during mutation. Maintaining or conclusion and step working is an important challenge that must be overcome for robot research tasks. As a typical multi-axis system, industrial robots usually require multi-axis to coordinate movement at the same time, which can reduce errors, ensure processing quickly, and improve processing speed, which is an objective production need. The motion stability control of the multi-action introduction robot can effectively ensure the safe and reliable operation of robot. At present, scholars in related fields have carried out research on robot mutation stability control and have achieved certain research results. Reference 1. The motion control of the introduction robot is realized, but its heading edge direction is relatively large. Reference 2 realized the rotation stability control of the introduced robot, but its rotation control takes a long time. Reference 3 proposed a multi-large neural network trajectory tracking control method for introduction robot based on interactive learning control, but not as well as in the simulation. Mainly as above problem, a mutation stability control algorithm for multi-axial introduction robot based on deep reinforcement learning is proposed. The mutation stability control of this method has better fault tolerance, higher accuracy, and higher effectiveness. The second part, research content. The mutation of multi-action introduction robot depends on the design of the overall structure of robot. The overall structure of a multi-action introduction robot is generally composed of a force net and legos. When the robot is in state moment. Its stability is usually judged by the supporting changing. The design of the single leg structure of the robot and the transmission mode of the drive direction affect the difficulty of the robot control agencies. The most important part of the design of the robot is the leg structure and the transmission mode of the drive. When the project point of the center of gravity on the support area is inside the support changing, the stability margin value is positive, and when it is outside the support change, the value is negative. The larger the stability margin value, the more stable the robot is. A structure feature design requirements of the multi-action introduction robot are built as shown in this figure. The leg structure not only needs to have sufficient strength and stiffness, but also needs to have a large load-bearing capacity so that heavy masses can be checked during work. Considering that the robot may face a variety of compact terrain environments, the robot needs to have good accessibility, and the single leg structure also needs to have a central button capacity. In addition, the single leg of the robot should also meet the requirement of simple structure, functionment, and easy control. The mutation mode of multi-axis introduction robot is used to first plan the mutation trajectory of the foot and they use inverse kinematics to calculate the angle of each joint, and finally use the servo control to release the joint positive servo. In the process of changing get the positive vector of the nominal point of the robot foot can be calculated according to the expected moment, velocity, and angular vector of the center of mass manipulated in advance. In order to adjust the gauge length with the speed of the robot, the calculation form of the gauge length is this equation. The position of the center point can be obtained from the body movement speed. So during the normal working process of the robot, the foothold should establish the following relationship. After the starting point, gauge length and swimming amplitude alone, the function equation can be used the cyclone function and the motion trajectory of the foot end is obtained as this. Considering the given moment speed and the directed moment distance, the operating foothold can be calculated. The disjoint foothold position is shown in this equation. In order to make the robot have higher stability, the swimming trajectory of the foot end needs to ensure that the speed at the initial moment of loosening the leg and the moment of nudge is zero, and it also needs to have a central height to overcome obstacles on the road. In the deep performance learning agencies, the action network is responsible for generating action, and the variable network is responsible for managing the general action. This method questions the relationship between the input factor and the correct state of the system and the result change in state input factor. This can be expressed in auxiliary differential equation as shown in this equation. Deep performance learning can conclusion learn is the interaction with the environmental. According to the Lagrange dynamic calculation method, the complex dyma- dynamic equation of the multi-action introduction robot is established as shown in this formula. First, it is accused that the robot is only affected by the ground force, and the robot can also be regarded as a part of its own gravity when it is loaded. The robot's floating base and four legs and the models as a whole, and the mass of the Legos is included. By describing that the rate of the change of the century magnitude is equal to the sum of the eccentricities. The centroid dynamical method can be established as shown in this formula, which is mainly used to evaluate the equation of different states and can be used to guide the selection of action. In order to be able to apply the model predict control axis, it is necessary to do some combination of multi-action introduction noble to build a convex model that can be used for linear optimization. The motion stability of the robot mainly refers to the performance that the robot always maintains a stable posture when moving under a perfect motion gauge. If a faulted robot needs to move forward, there must be an external force, and its external force is the friction and support provided by the ground. When the fuselage moves step in place or in the forward direction, it can be considered that when the airframe signal detects that the length speed of the body or the low end exceeds the upper image, the body is subject to a natural impact, and the natural impact stability control needs to be complex. The matic stability judgment of whether the state of the body has a terrain to alter can be explained as for this formula. According to the necessary consider of the nature impact control stability, nature state is the key to keep the robot body stable and counteract the natural speed. The expression form of the constant vectoring approach rate of the stability control algorithm is obtained as this formula. Choosing the close company control state of the minimum relax axis can not only establish inducting connection between each axis meet the requirements of multi-action simultaneous control but also limits the calculation amount of each axis. The third part, simulation analysis. The robot in this experiment is driven by 20 cars measured, composed of four egos with 3 degrees of freedom each. The master station writing its message into standard Internet data format and incorporate them into each kite data form. The robot hardware system is mainly composed of inter-ECU control computer, senior driver, robot joint battery, and remote interaction terminal. In the simulation experiment, the model of reference 1, the model of reference 2, and the proposed method are selected for comparative access. 5 groups of experiments were set up. Each group of experiments was carried out 20 times, and the average value was taken as the final result. The heading angle deviation, rotation, control time conclusion, and one-way adjustment distance of these 3 methods were respectively tested under the condition of 50 kg load pressure. Um, the composite result of the heading and deviation of the 3 methods are shown in this figure. It can be seen that the heading and direction of the process method is smaller than that of the method of reference 1 and reference 2, which indicates that the proposed method has a higher accuracy of the robot motion stability control. The time conclusion compared result of motion control of the 3 methods are shown in this figure. It can be seen that the method control time of the proposed method is relatively short, which indicates that the proposed method has high effectiveness in controlling the motion stability of the robot. The comparable result of the one-way adjustment distance of the 3 methods are shown in this figure. It can be seen that the one-way adjustment distance of the proposed method is short, which indicates that the proposed method has good annual tolerance for robot machine stability control. In summary, the proposed method can effectively improve the accuracy and effectiveness of motion stability control. The last part, conclusion. This paper states the rotation stability control algorithms of multi-action introduction robot based on deep reinforcement learning. By designing the structural feature of the multi-action introduction robot, the motion trajectory planning mode of the multi-action introduction robot is optimized. Based on the deep reinforcement learning opportunities, the robot motion equation is established at the motion stability control agency is designed by describing the change rate and of the center of mass. The experiments of reference results show that the motion stability control of the proposed method has good fault tolerance, high occurrence, and effectiveness. As a follow-up, we will continue to test the application effect on of the multi-action introduction robot mutation stability control systems designed this time in complex environmental. That's all. Thank you.